Hello all, welcome to my course on methods of adhesion measurement, theory and practice. As you remember, we are discussing contact mechanics, where we have indenters of various shapes and size, and they are indented against on an elastic half space, and we are considering cases without adhesion so far. We will continue this discussion today, and we are discussing axi-symmetric loading, where we started with point load on an elastic half space, and then we discussed about spatially distributed load, and we have discussed two different distributions. One is uniform, another is where p is equal to p 0, another is p 0 into 1 minus r square by a square square root minus square root inverse. So, these two pressure distributions we have discussed, and we have obtained the vertical and horizontal displacements or deformations at the surface of the elastic half space in the within the area of contact and also outside. So, we have discussed these things in the last class. So, today we will discuss another distribution of pressure onto this elastic half space, and that is given by this, where p is equal to p 0 into 1 minus t square by r square by a square square root. So, as you can see here that here in this case the pressure is maximum at the center at t is equal to 0 or r is equal to 0. Here t and r are actually equivalent, and I will just show you in a minute, and it is 0, p is equal to 0 where t or r is equal to a. So, this is the area, circular area in which axisymmetric circular area in which this indenter is indented on this elastic half space. What we are looking at is the surface of this elastic half space. And so, here we want to find out that how at a point B, which is at a distance r from the center of this circular area, what is the vertical displacement at this particular point. So, what we consider is that let us say there is an infinitesimal area which is given by this quantity c. So, that particular point c is at a distance s from the B, and this angle is actually phi. And so, what you want to know is that because of application of this infinitesimal load at c, okay, or this infinitesimal area, the area is given by s d phi into d s. So, the load is applied on this area. So, what is the vertical displacement at this point P, and then we will use this principle of superposition to integrate over the whole area, the load over the whole area. So, that is basically the idea. So, here this particular area point C or the small area C that at a distance t from this center. So, we need to express this t in terms of s over here. So, that we can do by considering that t square by writing something like this. So, the t square is equal to this is r plus this is s cos phi whole square plus s sin phi whole square, and that is equal to r square plus 2 r s cos phi is r plus s. Yeah. So, basically this square, this distance square plus this distance square is equal to this distance this is r, yeah. So, this distance t square, this is fine, plus s square. So, this is the way we can write t square. So, we can write p is equal to p 0, and we can write it actually a here, p 0 1 by a, p 0 should be 1 by a into a square minus t square. So, it is a square minus r square minus 2 r s cos phi minus here a square root. So, this should be the distribution on the of this pressure, and let us so that is the way you can write. Now, let us see that how to write. So, let us say total load on the area. Let us first calculate the total load on the area on the whole area. So, total load will be given as this is P here and P as a function of T, and let us say they have considered a small ring, that is 2 pi t is the perimeter into dt. So, this is an annular area in which the load is applied, and we are calculating the whole load over the whole area. So, that is given as 0 to a, and this is the total load, capital P is the total load. So, P t 2 pi t into dt, and that is equal to P t is equal to P 0 here, and here it is 0 to a, and this is 1 minus this is t square by a square, and this is square root, and this is 2 pi. So, I can write here 2 pi over here, 2 pi here, and this is t here, and this is dt here. So, I can write t is equal to a, let us say it is sin theta. So, at t is equal to 0, at t equal to 0, theta is equal to 0, at t is equal to a, theta sin theta is equal to 1. So, theta is equal to pi by 2, that should be the limit. So, within that limit we can integrate. So, here this p will be equal to 2 pi, this is p 0, and this is 0 to this is pi by 2, and this is t is equal to a sin theta. So, t square by a square is 1 minus sin square theta, this is cos square theta, this is cos theta. So, here I have is cos theta, and dt will be equal to a cos theta into d theta. So, it will be dt will be like, so t is equal to a sin theta. So, here a sin theta here, and then dt is equal to a cos theta. So, a cos theta here d theta. So, this is the way I have. So, I have 2 pi p 0, that is fine. So, t is equal to a sin theta, that is here, and 1 minus t square by a square square root. So, t square is 1 a square sin square theta, and divided by a square. So, 1 minus sin square theta, this is cos square theta, this is cos theta, and then dt is equal to a cos theta d theta over here. So, here then I will have 2 pi, this is p 0, and this is a square here, a into a square, and this is 2 here. So, 2 cos square theta is 1 minus 2 cos square theta, 2 cos square theta 0 to pi by 2, 2 cos square theta is equal to 1 plus cos 2 theta, 1 plus cos 2 theta and cos theta d theta. So, let us see. So, here dt is sin theta. So, here I could have to be, here the whole thing I have written here, a sin theta dt cos theta d theta a cos square theta. So, we can write it as both as cos square theta here, also as sin theta cos theta both. So, I have done it a little differently, but it comes out to be like this, and a square by 4 here. Okay. So, let us first calculate the total load on this area, and that can be calculated by writing as P is equal to, it is first considering a ring with thickness of dt. So, the area of that ring will be 2 pi t into dt, the pressure that applied is P. So, that is P 0 into 1 minus t square by a square, and this is square root, and the whole area I have to consider. So, 0 to a, because t varies from 0 to a. So, here therefore, I have it is 2 pi into P 0 into 0 to a, this is t here, and 1 minus t square by a square square root dt. So, let us take t is equal to a sin theta. So, that at t is equal to 0, at t is equal to 0, theta is equal to 0 here, at t is equal to a, theta sin theta is equal to 1. So, theta is equal to pi by 2 here. So, here I have p is equal to 2 pi p 0, this is 0 to pi by 2, and here I will substitute for t as a sin theta, and 1 minus t square by a square will be equal to t square by a square is sin square theta, and 1 minus sin square theta is cos square theta. So, square root of that is cos theta, and dt will be equal to a cos theta d theta. So, here dt will be a cos theta d theta. So, therefore, I have here 2 pi a square p 0 0 pi by 2, this is sin theta cos theta into cos theta into d theta. So, see here sin theta cos theta can be written as 2 sin theta cos theta can be written as sin 2 theta. So, therefore, it will be pi a square p 0 0 to pi by 2, this is sin 2 theta cos theta and d theta, and this is sin a b. So, we can write here 2 here and 2 sin a b. So, 2 sin a b will be sin a plus b plus sin a minus b. So, we can do all that and we can finally calculate the total pressure. So, here I have up to this a square by 4 2 sin theta 2 theta cos theta, and finally, it will come out to be a square by this a square by 4 sin 3 theta plus sin theta d theta, and by integrating that it will be minus 1 by cos 3 theta and sin theta will be minus cos theta. So, finally, I have here this limit from 0 to pi by 2 here, and this is 2 pi p 0 and a square by 4, that is what it comes out to be, and minus 1 by 3 cos theta minus cos theta, and if I use all the limits, so I will get finally 2 pi p 0 a square by 4 plus 1 by 3 plus 1, this is 4 by 3. So, it comes out to be like this 2 pi p 0 a square by 3. So, p 0 can be written in terms of capital P and a square as something like this. P 0 is equal to, it will be 3 p by 2 pi a square, okay, like that, 3 p by 2 pi a square. So, like that this p 0 can be written or p 0 can be replaced. So, now here I have we have to find out the deformation at this particular point B because of this infinitesimal loading at C, and that can be given as 1 minus sigma square, that is the Poisson ratio, divided by pi e, and this is P s ds d phi. So, we know that there is an s here, there is an s here, this s has got cancelled. So, we have gone through this in the last 1 or 2 lectures, and finally, I have something like this. The expression for t I have already derived, and so therefore, taking this a outside, I have this particular expression. So, here I need to do this integration in order to find out this vertical displacement v at the surface. So, here this s varies from 0 to s1, and this s1 can be found out something like this. How I did I write that? Let me just go through quickly. It is this s1 is a solution of the following equation: a square, that means from here to here, a square is equal to, this is r plus s cos phi whole square plus s sin phi square. So, if I just expand it, it will be r square plus 2 r s cos phi plus s square, okay. And so, you can write it as a square plus 2 r s cos phi plus r square minus a square is equal to 0. So, the solution of this equation, okay, will give the value of S1 as something like this, and since S1 varies from 0 to S1 here, 0 to the here, S varies from 0 to S1 here, the angle phi has to vary from 0 to 2 pi, the whole range. So, therefore, it is 0 to 2 pi is the limit. So, here we need to calculate this integration, keeping in mind that S1 is equal to something like this. So, here what you do is we write it as a square minus r square sin square phi minus r cos phi plus s whole square. So, this quantity that you need to find out, we need to write, you can write it like this: a square minus r sin square phi minus r cos phi plus s whole square. So, this quantity I write it as a square, and this quantity I write it as x. So, therefore, what I have is square root of a square minus a square square root. So, the integration of this quantity is given as x by 2 square root of a square minus a square plus a square by 2 sin inverse x by a. So, that is a known result, that is from maths handbook one can get. And so, therefore, we can substitute the expression for x from here. So, I have r cos phi plus x is equal to x here, that is x here, and a square is equal to this quantity minus x square. So, if I write a square minus a square, so I will have the whole thing over here, whatever I have here, plus half a square by 2. So, that is half a square by 2 here, and sin inverse this quantity. So, that is the way the integration turns out to be. So, here I have this expression, and the integration limit is between 0 to s1. So, if I write the integration limit, it will be r cos phi plus s1 by 2 square root of a square minus r square minus 2 r, this is s1 here, s1, because this s1 I am writing here, then cos phi minus s1 square plus a square by 2 sin inverse, this is r cos phi plus s1 square root of a square minus r square sin square phi, and then minus now I have to write for s 0. So, it will be r cos phi by 2 and to square root of, it will be a square minus r square, because now s is equal to 0 plus a square by 2, this is sin inverse, and remember that s is equal to 0 here. So, it is r cos phi by square root of a square minus r square sin square phi, like that. So, now what is this quantity that we can write? So, this is a square minus r square minus 2 r and s1 cos phi minus s1 square. Now, this quantity, now s1 is given as what? That was from the previous slide. So, s1 is given as minus this quantity, s1 plus s1 is equal to minus r cos phi plus square root of a square minus r square sin square phi. So, this is s1 is equal to minus r cos phi plus square root of a square minus r square sin square phi. So, if you can see here that if I write here s1 plus r cos phi, if I wrote the whole square of this whole quantity, that will be actually, this quantity will come out to be actually equal to 0. This quantity comes out to be equal to 0, because this s is a solution of s1 is a solution of this equation only. So, therefore, this term will be equal to 0. So, this term will come out to be 0 here plus this term over here now. So, this term is actually equal to 0. Now, over here r cos phi plus s1 here. So, this term is a square by 2 here into sin inverse, this is r cos phi plus s1. So, r cos phi plus s1, that is square root of a square minus r square sin square phi divided by square root of a square minus r square sin square phi. So, notice that this is equal to 1. So, this sin inverse 1 is pi by 2. So, this quantity will come out to be a square by 2 into pi by 2. Like that we can simplify all the terms. Now, here this particular term, okay, we need not worry about this term and this term, because when we integrate from 0 to phi with respect to phi 0 to 2 pi with respect to phi, this term will fall out. So, like that if we consider all that, we will have only this term that is of consequence, and so therefore, finally we will have this term only we have. So, this is pi by 2 and this is 2 here. So, it is pi by 4 and a square is written as this quantity, a square is like this. So, this we can integrate easily, and one can actually find out that this v comes out to be like this expression. So, here this integration can be done, because sin square phi here it can be easily calculated. So, this is the whole idea here, that the vertical displacement on the surface is given by this expression. Now, what about the horizontal displacement? So, remember I had discussed this also in the last class, that here for example, the load is being applied over here. So, the horizontal displacement for this particular point, for this because of this load will be along this direction, right, because that is the way, because vertical load, the low pressure is being applied on this point. So, because of the load here, the horizontal displacement at this point will be in this direction. Now, we need to consider the cos term of here, because the other sign terms, okay, that will get cancelled when you integrate over the whole phi from 0 to 2 pi. So, therefore, we have this cos phi, this particular term over here, and if we integrate whole thing, we will get the result. So, I am not doing the whole thing after integration. So, it comes out to be something like this. So, that is the way to estimate the horizontal and the vertical component of this deformation or displacement at this particular point B. And so, we can actually summarize the results for different type of pressure distribution, okay, within the area of contact, and this is outside the area of contact. So, this is table summarizes all the results that we have derived, and this part I have kept as an assignment. So, you can take it, you can try to derive it on your own. For this kind of particular load distribution, what will be the vertical displacement at a point which is outside the contact area. So, you take it as an assignment and try to do that. So, here at r is equal to 0, what will be the displacement deformations. So, it is summarizes these results. This can directly obtain by writing r is equal to 0. Remember that this is the elliptic function of second kind, where r is equal to 0 gives rise to pi by 2. So, we can substitute here pi by 2 over here, and you can get this expression like that. So, now I will take up few problems to which will clarify the ideas further. So, let us say rigid axi-symmetric indenter is pressed against a compressible elastic layer of thickness 20 millimeter. So, this is a 20 millimeter thick layer, okay, and a load controlled experiment when the applied load on the indenter reaches 3.143 Newton, the radius of the circular contact area. So, basically there is a indentation that happens and there is a circular contact area is measured to be 1 millimeter radius. So, radius is 1 millimeter and this is the thickness h. So, as you can see that the h is much larger than r. So, we can say that this is indeed an elastic half space. So, we can you can use the relations or the results that we have so far derived. Now, at this load the radial and vertical displacement of the layer is measured at the center and at the periphery. So, basically there is a center here and the periphery here at which this vertical and horizontal displacements has been measured and has been obtained over like this. This is the data that has been obtained. So, assuming negligible adhesion. So, basically the kind of problem that we are so far we are discussing here between the indenter and the layer, obtain the Poisson ratio and the Young's modulus of the elastic layer, that we need to find out. So, we have to do it from the data that is given. So, let us say that the V at z is equal to 0 and this is at r is equal to 0, that is given, and let us say this is V at z is equal to 0 at r is equal to this is 1 millimeter. So, it is actually the periphery that is given. So, let us say what is the value that we get. So, it is 1.68 divided by 1.07. Okay. So, if you see this ratio and we can find out, we can use the calculator. So, it comes out to be about 1.57. Okay. So, as you know 1.57 is very close to pi by 2 here. So, that gives an idea that what may be the kind of pressure distribution that is there that has given rise to this kind of deformation. So, we need to first, because in this problem the type of the loading that has not been, the load distribution that has been mentioned. So, we need to figure that out first. So, therefore, over here you can see here the vertical displacement at r is equal to 0 divided by that at periphery, okay, comes out to be pi by 2, and we know from the results that we just presented that this V by V0 okay, for this particular case, okay, it comes out to be pi by 2 V at r is equal to 0 and divided by V at r is equal to a. So, what it means that the kind of loading that has given rise to this kind of these deformations, okay, it turns out to be, it will be P is equal to P0, that is uniform loading. Okay. No other type of loading has this value close to this, 1 and 2 is the other two cases. So, it is actually this particular type of loading that has been applied. So, we can find out the total load that has been applied is 3.143 Newton. So, we can find out that what is this P0 over here. So, here the P is the capital P is the total load. So, therefore, P0 is P by pi a square, and that if I write that for value of A is 1 millimeter, this comes out to be about 1.10 to the power 6 Newton per meter square. So, it is like that. Now, we need to find out the elastic modulus and also the Poisson ratio. So, that we can find out again using the data that have been given. For example, over here at r is equal to A, okay, this value of E of r is equal to 1, okay, E of at elliptic function as second order at second kind at r is equal to A, this value is equal to 1. So, therefore, this is the value at the periphery for this, and for this case it is this. So, therefore, like let me write that as u by v at z is equal to 0 here, z is equal to 0 here, and at r is equal to A here and r is equal to A here. So, that will turn out to be, this is minus 1 minus 2 sigma by 1 plus sigma, this is P0 A by 2 E, and over here this is 4 into 1 minus sigma square P0 A by pi E. It is like that. So, therefore, we can simplify it. So, this is 1 plus sigma by 1 minus sigma square will be 1 minus sigma, this is P0 A, P0 gets cancelled, E and E gets cancelled over here. So, it is minus 1 minus 2 sigma by this is 4 into 1 minus sigma over here. This is what I get, or pi also I have, this is pi by 2 actually, this is pi by 8 in fact, because this is E here, E here. So, this whole thing will be, so that from the data that has been given here, that is u by v at the periphery. So, that is the result 0.14 by 1.07. So, this is minus 0.14 by 1.07. This is u by v minus 1.07. So, we used all that, and we can now put the value of pi and all that, and we can get here, here we can get, this is the one I got here. So, by putting the value of pi and all that, doing little the calculation, we found that sigma, that is the Poisson ratio, comes out to be 0.4. And now let us say, so Poisson ratio 0.4. Now, elastic modulus want to calculate, and for that it is easy, we just need to see any of the results. So, let us say we consider this result, that experimental data that we have, and where this V at periphery is 1.07 millimeter, and that is from here. So, now I have here all the values, I know P0, I know A, I know this sigma value here, and I can calculate E very easily, and that comes out to be about a megapascal 10 to the power 6. So, I hope you can follow this calculation over here easily. Let us take another problem, in which case we have this, an elastic half space is subjected to a uniform load P is equal to 200 Pascal. So, here it is given that a uniform load applied over an annular area defined by R1 is equal to 2 millimeter. So, this is actually 2 millimeter R1, and here it is 4 millimeter, it is R2 here. So, the material properties are 10 megapascal, and it is Poisson ratio 0.25. Determine the vertical displacement at the center of the annulus, or that is r is equal to 0 at a point on the outer edge of the annulus. So, at this particular point. So, how do I solve it? So, we have to consider here that the, as if that the load is being applied. So, load is being applied through the shaded area only. So, what we consider, we will use this principle of superposition. So, we will consider that V at z is equal to 0 because of the area through which the load is applied, that is A. So, here it is compressive minus V at z is equal to 0, okay, and this is area B, let us say it is tensile, something like that. So, if I subtract the vertical displacements because of these two different loading at two different areas, okay, we will get it. Only thing we need to know, we need to be careful about that when you are considering at r is equal to 0, okay, this particular point is within the loaded area for both the loading type and both the circles or both the contact areas. However, when you consider this particular point C, okay, the C is lying within the area of loading for area A, but within the outside the area of contact for the area for the loading area B. Okay. So, we need to be careful about that, but otherwise we can easily estimate. So, let me do it for the r is equal to 0 here. So, for example, that vertical displacement, okay, this we know will be given by something like this. So, therefore, the net vertical displacement that will be equal to here this 4 into 1 minus sigma square by pi e, and at e 0 it is pi by 2. So, that will be the same for both. So, it is pi by 2 here, and the a for the outer one, it is for the a, that is r 2 minus r 1. Okay. It should be like that, and that should give you the value of the vertical displacement at the center. Okay. So, it is like this. So, here we are. So, this is pi gets cancelled and p 0 is already given. So, finally, we get here to be 0.75 micron. On the other hand, when you consider, let us say this power point at point C, due to positive pressure on circular area A, vertical displacement will be like this. So, this is positive pressure. So, this you already know, and for the negative pressure circular area B, remember that this point for the circle B, this particular point lies outside the area of contact. Okay. So, therefore, we have to use this relation over here. So, this is there in the table. So, this is the elliptic integral or integral of the first kind. This is the elliptic first kind, the second kind, and these values can be obtained. Okay. These values k at a by r and e of a by r, these values can be obtained, and we can substitute those values and we can write that. Okay. So, here remember that a here it is r 1 is 2 and r 2 is equal to 4 here. So, as a result it will be r 1 by r 2 will be 0.5, okay, 0.5, right, because it is just outside the contact area. So, here finally after doing all the algebra we can do, and we can use the value of k at 0.5. So, this value will be about 1.68575, and E at r 1.5, that value comes out to be this. So, using all this we can finally get that V for this case comes out to be 0.194, but this is in the tensile load because we have to subtract it. So, therefore, it is minus here. So, 0.955 minus 0.194 gives us 0.761 micron. So, that is the actually the result. So, actually the result that is there. So, this is the amount of vertical displacement that will be there at that particular point. So, today I will stop here. Thank you all for your kind attention.